Nobody was supposed to find it. That's the part that never makes the headlines, buried under press releases and carefully worded scientific abstracts. Nobody was hunting for an object like this. The telescope that caught it was pointed at the sky for a completely different reason, scanning for threats, for rocks that could end cities, for debris on collision. Courses with Earth. It was doing its job. Then, on the morning of July 1st, 2025, at the Atlas Survey Telescope in Rio Hurtado, in the high-altitude desert of Chile, an automated system flagged something that had no business being where it was. A faint smudge of light moving too fast, moving on a path the software had no category for, because the software was built to track objects that belong to our solar system. This one did not. Within hours, the data was in the hands of astronomers around the world. Within a day, the verdict was unanimous. The object was given a name, 3I Atlas, the third interstellar object ever confirmed in recorded human history, a traveler from another star system, already deep inside our solar neighborhood, moving at roughly 130,000 miles an hour on a hyperbolic path that would carry it through the inner solar system and out again, never to return. Let's go back further because the story starts before anyone noticed. NASA's TESS satellite, the transiting exoplanet, survey satellite, an instrument built to stare at stars, looking for the flicker of distant planets crossing in front of them, had actually recorded 3I Atlas on its detectors between May 7th and June 2nd, 2025, 55 days before the official discovery date. The data existed. It sat in an archive, unflagged, unremarked upon, while the object it had captured moved steadily deeper into the solar system. Our planetary-defense network, the system built specifically to give us early warning of approaching objects, had unknowingly photographed an interstellar visitor nearly 2 months before anyone realized what they were looking at. If 3I Atlas had been smaller or darker, or arrived at a slightly different angle, it might have completed its entire passage through the inner solar system without a single telescope ever identifying it. We would never have known that something ancient and foreign had drifted through the space between our planets. Think carefully about what that implies for how much we actually know about what passes through our own neighborhood. The designation tells you everything about the context. The I stands for interstellar. The 3 means this is only the third such object ever confirmed in the history of astronomy. The first was Oumuamua in 2017, a strange elongated object that tumbled through the solar system producing acceleration. No ordinary comet should produce without a visible tail. Scientists argued for years about what it was and never fully agreed before it became too faint to study. It was gone within weeks of discovery, and by the time researchers had assembled enough theories to seriously test, the object itself was already unreachable. The second was Borisov in 2019, a more conventional, comet-like visitor that gave scientists their first genuine chemical sample from another star system, one that fit reasonably well into existing frameworks built from decades of studying our own solar system's comets. 3I Atlas was neither of those things. It was larger than both, more active than both, and it carried a chemical signature that made Borisov look almost familiar by comparison. The orbital eccentricity of 3I Atlas was measured at roughly 6.1. For reference, a perfectly circular planetary orbit has an eccentricity of 0. A parabolic escape trajectory, the minimum needed to leave a solar system entirely, has an eccentricity of 1. An eccentricity above 6 means this object was never gravitationally bound to our sun in any sense. Its velocity was so far in excess of anything the sun's gravity could have produced that the energy in its trajectory had to have originated somewhere else entirely, deep interstellar space. Another star system, possibly a region of the galaxy, no telescope has ever studied up close. Its excess velocity, the speed it carried purely from its own interstellar momentum, before it ever encountered the sun, was measured at roughly 58 kilometers per second. About 130,000 miles an hour of pure momentum accumulated over an unknown journey through the galaxy. Even after the sun's gravity pulled and accelerated it further at closest solar approach, that underlying interstellar velocity remained encoded in the shape of its path, and the math pointed backward toward the direction of Sagittarius, toward the inner galaxy, toward a region of the Milky Way far older than anything in our immediate stellar neighborhood. This is where the story shifts from unusual to genuinely difficult to explain cleanly. 3I Atlas arrived on a retrograde orbit, moving in the opposite direction to every planet circling our sun, counter to the rotation of the solar system itself. And that retrograde path happened to align with the ecliptic plane, the flat disk defined by the orbits of the planets, to within about 5 degrees. Researchers, most prominently Harvard astronomer Avi Loeb, calculated the probability of an interstellar object arriving from random interstellar space and landing within 5 degrees of ecliptic alignment purely by chance at roughly 0.2%, less than 1 in 500. For context, when scientists find a 1 in 20 probability turning up in experimental data, they usually consider it worth a second look. This was 25 times rarer than that. It's worth being precise about what this number does and doesn't mean. It describes how statistically unusual the alignment is under a model of random interstellar arrival, not proof of anything beyond that the alignment is genuinely rare. Most planetary scientists studying the object treat it as a striking coincidence worth investigating rather than evidence of intent. And NASA has been direct in stating there is no evidence the object is anything other than a natural comet. But the number itself, and the fact that nobody has produced a fully satisfying natural explanation for why the alignment happened to land this close, is real and undisputed. And the trajectory wasn't even the most unusual thing about this object. That came from the James Webb Space Telescope. Webb first observed 3I Atlas on August 6, 2025. Getting Webb to track the target at all was a genuine technical achievement, since the telescope was designed for deep field observations of galaxies billions of light years away that might as well be motionless, not for tracking a comet crossing the inner solar system at 6 figures of miles per hour. Engineers had to build new tracking protocols on the fly to keep the object centered in Webb's field of view. When the spectrograph data finally came back, the lead scientist on the observation team described the spectrum as having left him blown away, a phrase that made its way into the formal published record, which tells you something about what the instrument actually found. Webb's near-infrared spectrograph showed the coma, the cloud of gas surrounding the heated nucleus, dominated by carbon dioxide rather than water vapor, the volatile that overwhelmingly dominates the coma of nearly every solar system comet as it warms near the sun. The measured ratio of carbon dioxide to water was roughly 7.6, about 4.5 standard. Deviations above the trend seen in every long period and Jupiter family comet ever cataloged in our own solar system. That is not a small deviation in scientific terms. Independent confirmation came from 3 separate instruments: Webb, NASA's SphereX mission, and the MAVEN spacecraft orbiting Mars. All 3 agreed. The carbon dioxide to water ratio in this interstellar visitor was categorically different from anything that has ever condensed and frozen in our own solar system's planetary formation disk. Then Webb came back for a second look. In December 2025, as 3I Atlas swung away from the sun after its closest solar approach and moved outward through the solar system, the Webb team pointed the mid-infrared instrument, MIRI, at the comet. On 2 separate occasions, December 15th and 16th, when the object was roughly 205 million miles from the sun, and again on December 27th at about 236 million miles out. The results were published in the Astrophysical Journal Letters in April 2026 and announced by NASA that June. The headline finding was the first direct detection of methane on any interstellar object in the history of space exploration, methane frozen deep inside a nucleus that formed before our solar system existed, released now, billions of years later, as the warmth of an unfamiliar star reached into its ancient core for the first and only time. Because the methane emerged well after the comet's closest pass to the sun, when most volatile release typically declines, researchers concluded it must have been buried deep beneath a thick, insulating crust, only reaching the surface once heat had time to penetrate that far down. The proportional chemistry stopped astronomers as much as the methane detection itself. When Webb mapped the spatial distribution of the gases, where the water was concentrated, where the carbon dioxide was releasing from, where the methane originated, the picture was of a layered, chemically differentiated structure. Methane and carbon dioxide concentrated near the nucleus, water vapor spreading much further out into the surrounding coma, consistent with sublimating from icy grains, rather than the surface directly. And this wasn't a uniform, homogeneous ball of dirty ice. This was a structured object with distinct interior layers, preserved in deep interstellar freeze for what turned out to be an almost incomprehensible span of time. Follow-up observations from the Subaru telescope in January 2026 added another layer. The carbon dioxide to water ratio had measurably dropped between Webb's earlier observations and the later Subaru data, confirming that an outer carbon dioxide-rich shell had partially depleted during the comet's exposure to solar heating. The interior chemistry was different from the exterior. This object had layers of hidden composition that even the sun's heat had only partially uncovered by the time it left, and separate research from the Royal Belgian Institute for Space Astronomy proposed that this layered structure itself was the product of billions of years of exposure to galactic cosmic rays, which had slowly converted the outermost 15 to 20 meters of the nucleus into an irradiated, chemically altered crust, while leaving the deep interior essentially untouched, a frozen, pristine record of conditions in a stellar environment humanity has never directly observed. But here's the finding that changes the entire scale of the story. Isotopic measurements, captured by Webb and the ALMA Observatory in Chile, later supported by follow-up spectroscopy from the European Southern Observatory's Very Large Telescope, carried what amounts to a literal chemical timestamp, written into the ratios of deuterium and carbon isotopes trapped in the comet's frozen volatiles. Isotopic ratios in comets reflect the environment in which they formed, the temperature, the density, the elemental makeup of the protoplanetary cloud that condensed around whatever star gave birth to the object. The comet showed roughly 30 times more deuterium than typical solar system comets, an enrichment that, according to our understanding of astrochemistry, can only occur in an extraordinarily cold environment. One Belgian researcher, Romain Maggiolo, and his team calculated at around 30 kelvins, roughly minus 405 degrees Fahrenheit. Peer-reviewed analysis published in Nature in 2026, led by Maggiolo at the Royal Belgian Institute for Space Astronomy, concluded that 3I Atlas likely formed somewhere between 10 and 12 billion years ago. The universe itself is only 13.8 billion years old. Our sun has existed for about 4.6 billion years. Every object ever cataloged in our own solar system formed at roughly the same time as the sun. This comet was already ancient when the cloud of gas and dust that eventually became our sun had not yet begun to collapse. It formed in the early Milky Way, in the frigid outer reaches of a star, a system that almost certainly no longer exists in any recognizable form, its chemistry locked in place by billions of years of cold, dark isolation. And it passed through our solar system in 2025, while, for the first time in that entire span, we happened to be watching. The Mars chapter of this story deserves more attention than it's generally received. When 3I Atlas swept within about 29 million kilometers of Mars on October 3rd, 2025, it triggered one of the largest coordinated multi-spacecraft observation efforts ever directed at a single interstellar object. ESA's Mars Express and the ExoMars Trace Gas Orbiter repositioned their instruments. NASA's Mars Reconnaissance Orbiter, carrying the high-resolution HiRISE camera, locked onto the comet. China's Tianwen-1 orbiter captured its own images using its high-resolution camera, showing the comet's coma and tail against the stellar background. And on the surface of Mars itself, the Perseverance rover tilted its Mastcam-Z camera skyward on command from Earth and photographed an interstellar object from the surface of another planet, a first in the history of space exploration, even though the object was so faint from that vantage point that the resulting images required extremely long exposures, faint enough that stars streaked into lines while the comet itself remained barely visible. This was humanity observing a visitor from another star system from two planetary surfaces simultaneously, something that will likely be written about for generations, regardless of how the underlying chemistry gets ultimately. It's worth being precise here, because this is exactly the point where headlines tend to exaggerate. The minimum orbital intersection distance between 3I Atlas's path and Mars's own orbit was calculated at about 0.08 astronomical units,